Hello, I'm Min Song from Function Bay Incorporated in South Korea. I am pleased to present a case study at International CA Conference. At the same time, I'm feeling sorry that this conference is being held in non-face-to-face edition because of COVID-19. The topic I'll be presenting is a study of verification using co-simulation of dynamics and particle method for a tractor mid-more behavior. Then from now on, I'll start my presentation. Recordine is an interdisciplinary CA software based on multi-body dynamics background. Recently, as particle methods have been actively commercialized and being used a lot, FunctionBay has developed a dedicated interface for Recordine, which makes it interactive with a couple of particle-based software. It allows more convenient user interface for analysis, especially such cases where mechanical systems interact with fruit or grains. Currently, Recordine is able to interact with a few famous particle-based software like Altair EDEM and Particworks, and it is expanding its coverage in a variety of application areas, such as the example video shown. From last year, this dedicated interface is available not only for rigid bodies but also flexible bodies, and we are looking forward that the scope of this multi-physics application will more widely spread out. I have researched this case study by myself using some technical procedure in this page, and the details will be talked from next page. In the chapter 1, I'll explain a background of the research briefly. This research started from a request for an agricultural machinery company in South Korea. The biggest background of research is that they have a need to verify the behavior of tractors mid-more using an analytical method. For your reference, the mid-more is located in the middle of the tractor and have a role to mow the grass by landing on the ground. Although it is possible to analyze the dynamics model of a tractor sufficiently well with General Dynamics software, but there was no good way to model and analyze the grass among any commercialized CA software. So in this research, I tried to do analysis of the grass behavior as well. A multi-body model of the tractor was modeled using Recordine, and Altair EDEM was used for modeling the grass. And through co-simulation between poles, the grass is cut by rotating blades of the mid-more. Next, in the chapter 2, I will explain the dynamics model for a tractor in detail. The dynamics model for the tractor is composed of a few subsystems such as a working module, a mainframe, a powertrain, and tires. Here the working module is the mid-more. Blades in the mid-more rotate by a belt system which transmit the rotating force from a PTO, which they call power takeoff. The frame is composed of an engine frame, a center frame, and a sheet module. Some of the pre-jobs for CAD model simplification was done removing unnecessary components from the assembly. And the powertrain consists of an engine, a transmission, PTO, and a housing and some others. And there are 4 tires. I could get all material properties of components and put them into the tractor model through Recordine GUI. And finally, I have compared the total weight of components and the real weight of the tractor which I got from the product spec, and I could make sure both weights are almost the same. By this comparison, I could confirm the Recordine model has been properly built up and prepared. The tractor model is more complicated than I thought. In spite of the CAD model simplification by pre-jobs, the entire model is built up with 72 dependent bodies, 77 joints, and 55 force elements for the power transmission. And the gearbox is modeled using coupler joints between many gears to decrease the time for contact calculation. For the tire modeling, the UA tire model in Recordine G tire module was used. Basically, the dimensions tires are like in the tables on the right hand side, and the other necessary parameter value of the tire were also applied for more accurate performance. These values I received from the customer. Then in the chapter 3, I'll explain about the model upgrade with flexible bodies. This page shows the input condition and an additional modeling for driving analysis. The tractor model's input parameters are for driving motion of the rotating output shaft of the engine. The rotation speed of the output shaft is 850 rpm. By transferring power from the engine, 4 wheels are driven. For setting the mid-more on the ground, a Recordine on-off joint will be activated after 5 seconds from the start. The lower right picture shows the seated mid-more. Now we can see the simulation result through two animations. One is the result of straight line drive, and the other is slalom drive on curve path. So I could finally be sure about the feasibility of the multi-body dynamics model built by Recordine. A component was converted to a flexible body in the original model. It is the shaft of belt pulley on the center position of the mid-more assembly. The flexible body was meshed with the Tetra elements, and 4 rigid body elements were connected using Recordine Automesher, and the flexible body is converted from the meshed full flex body to a new Alflex body having natural modes of deformation and some of interface nodes information based on the eigenvalue analysis method. Now, you see the simulation result showing the stress variation and the maximum stress on the shaft when the mid-more is loaded and seated on the ground. We could see just small stress value on the shaft around 2 or 3 megapascal. At this chapter, I explained the grass modeling using particle method using Altair EDEM. For the grass modeling using Altair EDEM, I followed a process in this slide. At first, I did a grass modeling considering the suitable size and the number of particles per single glass. Then I created a CAD model for the grass root which hold the grass from the ground. At next step, I finalized modeling of a set of grass, defining the property of material for the grass part and the root. Next, I ran a simulation with the single grass model in Altair EDEM to generate the real characteristics of the grass. Finally, I copied the single grass model and pasted it many times on the ground to array them as a group of grass fields. Let's see more in detail about the whole process on the grass planting. Before getting into the modeling of grass field using software, I needed to plan and decide beforehand the whole size of the grass field, according the total size and the number of grass and the gap between individual grass. I have to select any suitable size of grass and the array for the entire field. So finally, I have decided the particle size for single grass and the gap between grasses and the total number of grass for the field. As the second step, I prepared some CAD geometry for the roots of grasses. This root will hold the grass, fixing them on the ground. Likewise, I needed the same array of root field, just like the grass field I considered at the previous step. Then I found proper values for modeling parameters. As you see in the figures, a grass is created with a series of DEM particles, and the adhesion between particles was defined by a special contact of Altair EDEM called bonding void contact. With some of parameter study for this grass modeling, I could create a fine particle-based model for the grass, and it represents the grass characteristics quite well. After preparing a grass model with DEM particles and the special contact and bonding force, I should run a simulation with the prepared grass model. A group of particles with a special adhesion force are showing very good and realistic grass behavior like this image. This step is so-called copy and paste of a grass model to the ground. As I planned at the first step of this procedure, I arrayed a group of grasses in an area I defined. In the chapter 5, finally, we can see the co-simulation between Recordine and Altair EDEM. In order to reduce the total simulation time, I planned the simulation scenario to start just after the midmore is seated on the ground. To the starting point, there needs 5-second upfront movement of the midmore from its initial position. So just with Recordine, first step of preliminary simulation from the initial to the seated position of the midmore has been done, and I extracted that position as another initial state of the midmore using a special Recordine function called initial condition export. With this special feature, we can extract and define a specific position or pose of dynamic model for running another simulation with the changed initial condition. Anyway, the co-simulation with Altair EDEM was started from the 5 seconds time frame with the new initial condition information of the tractor. Let's see the result with an interesting video. The particle grass are cut away by rotating blades of the mid-mower along the movement of the tractor on the grass field. The adhesive force within grass particles are broken by the impact force of rotating blades, and the reaction force are also exerted to the blades as well. Conclusion. Through this research, first, it could build up a dynamics model for a small tractor. This dynamics model can be used for co-simulation with DM particles. And secondly, a grass field was successfully modeled using DM particles and its special contact and bonding force. And I could figure out a feasible co-simulation modeling using Riccardine and Altair EDEM for the process of grass cutting with a reliable set of parameters. However, in this research, I couldn't do a correlation between the simulation and an experiment. So my future job is to do the correlation with an experiment with our customer. Thank you for listening to my presentation.